Hey, thanks for joining me. I'm going to show you how to do two different types of elevator problems in this video. The first one, we're going to figure out the apparent weight of the rider, and in the second one, we're going to figure out the acceleration of the elevator. So here's our first situation. We have somebody who has a mass of 80 kilograms. They're in an elevator that is going up, and it happens to be slowing down with an acceleration of magnitude 1.2 meters per second squared. And I want to figure out what their apparent weight is. In other words, if they were standing on a scale, what would the scale read? Now, I'm always going to start out a problem like this with a free body diagram. I always draw the force of gravity. Then I ask myself, where does the object contact something? So where is this person in contact with something? I usually highlight that in the picture as a reminder. And the only place where this person is contacting something is with the floor there, or if they're standing on a scale, it would be with the scale. That is going to exert a normal force because the electrons of the floor repel the electrons of the shoe. So I'm going to draw an upward normal force there. And that's it. So then we can go to our Newton's second law equation, which we're going to have the positive upward normal force, the negative force of gravity, and divide by the mass of the person. So now we're trying to figure out the normal force. Now to do that, we need to know the force of gravity. And of course, hopefully we remember our formula for the force of gravity, Fg equals mg. So this person's mass is 80 kilograms. The Earth's gravitational field strength is 9.8 newtons per kilogram. So this person has a true weight of 880 newtons. Now we can fill out the details of this equation here. And there's one little trick here, and it's the acceleration. Yes, it's 1.2, but is it positive or is it negative? So when we read the description, the elevator is going up, but it's slowing down. So if it's going up, that means its velocity is positive. When something slows down, its acceleration is always in the opposite direction of its velocity. So we have a negative acceleration here. Another way to think of that is that in order to make this thing slow down while it's going up, you would have to push down on it. That's the direction of the net force, negative, down. And that's always going to be the same direction as the acceleration. So again, it's negative. All right, so we're going to find the normal force. The force of gravity, as we calculated, is 880 newtons. The mass is 80 kilograms. And so we find out that the normal force here is equal to 688 newtons. In other words, the person feels lighter than their true weight of 880 newtons. All right, let's look at a second situation. And again, we have our person on an elevator. Here, it's a different person, so not necessarily an 80 kilogram mass. What we now know is that when the elevator is at rest, the scale reads 735 newtons. But when, well, I won't say whether it's accelerating or constant velocity or what, but at another point in time, the scale happens to read 795 newtons. So what I want us to figure out is, one, what's the acceleration at this other point in time? And two, let's see if we can figure out which way is it moving? Is it moving up or down? And whether it's speeding up or slowing down. Okay, let's start with the free body diagram. It's not going to be different than the last one we just did. We got a force of gravity pointing downward. There's your contact point. That's going to create a normal force pushing upward. That's your free body diagram. Newton's second law equation, same thing as last time. Positive Fn, negative Fg divided by m. So now, though, we're trying to figure out the acceleration, which means we need to fill in the mass and the force of gravity and the normal force. So it seems like we have a lot missing. The key here is that at rest, the scale reads 735 newtons. Well, if it's at rest, then the forces on the person have to be balanced. And so the normal force, which is what the scale reads, and the force of gravity are both the same number, 735 newtons. So now we know that the force of gravity is 735 newtons, and we can go to our force of gravity equation to figure out the mass. So 735 is equal to m times 9.8. The mass of this person is 75 kilograms. Okay, let's plug this into our equation to figure out the acceleration. So the acceleration is equal to the normal force, in this new situation, if the scale reads 795 newtons, that's the normal force. Oh, it's the end of fourth period. Go home or keep watching, whichever. 795 newtons is the normal force. That's how much the scale is pushing upward with. So that's what the scale reads. And Fg is 735 newtons, and the mass is 75 kilograms. And so when you do all of that calculation, you get a positive answer, which I did not do ahead of time. So I'm cranking this out on my calculator right now. Isn't this exciting? It looks like we get positive 0.8 meters per second squared. That's the acceleration at that moment in time. All right, so is it going up or down? Is it speeding up? Is it slowing down? Think about that for a little moment. And maybe pause while you come up with an answer for that, and then you can turn the video back on and I'll tell you the answer. Okay, so is it going up or down? Well, the answer is you can't tell. Not enough information. Same thing about speeding up or slowing down. You can't tell. Not enough information. Why not? All we know is that the acceleration is positive. There's literally no other information here other than the acceleration is positive. So there's actually two situations where a positive acceleration can occur. One of those situations is if you are moving upward and you have a positive velocity and you are speeding up. Because remember, when you speed up, velocity and acceleration always point in the same direction. But potentially, what if we're moving downward? Can you have a positive acceleration when you're moving downward? Yeah, you can. That would be if you're slowing down. When you're slowing down, velocity and acceleration are in opposite directions. So all we know is there's a positive acceleration. And unless we know something more, we can't tell whether it's moving up or moving down, which means we also can't tell whether it's speeding up or slowing down. All right, see you next time.